So I will be providing the introduction to stochastic numerics. I will start off with a quick review of the study of numerics in the deterministic case. I will then discuss the Euler-Maruyama method, and then the convergence of such solutions, and then finally I will discuss an introduction to the general Taylor schemes. So the simplest case we'll discuss is the Euler method. It's simply just a truncation to first order of the Taylor series. We can get a local error from just the fact that we're taking discrete time steps. The convenient thing is that for the local error, we can use Taylor's theorem to get a bound on the local error. And the more difficult case is actually finding the global error. So for this case, what we do is we just impose a Lipschitz condition, and we find that the local error is order delta squared, and the global is simply delta. So we can also define implicit schemes. Implicit in the sense that the iteration shows up on both sides of our equation. And so one of the ways to get around this is to actually use the Euler method to find an estimate for xn plus 1, and then plug back in to get a correction on that estimate. And so that's why this is known as a predictor-corrector method. And so for this case, if we actually do this kind of improved Euler method, we find that then the local error is actually delta cubed, and the global error is delta squared. And so the convenient thing about these implicit schemes is that generally they're going to be much more stable than explicit schemes. And so you're going to find that that's way more useful if you have, for instance, a stiff system that could blow up without you really knowing. So now returning to our wonderful stochastic calculus, we find that sort of the natural extension of Euler's method for ODEs is the Euler-Maruyama method. And so this just gives the iteration in terms of essentially what you'd expect, the SDE. However, in this case, we have an added term, and that term, delta W, we can simulate just by drawing it from a Gaussian distribution with mean 0 and variance delta t. So there are many different reasons why one would want to study an SDE or simulate it. And so for that reason, we have different levels of convergence. So the first type is strong convergence. What you can really think of this is pathwise convergence. And so what that means is that in the limit, as we make our step size goes to 0, our actual paths should approach the path that we would have gotten from the same iteration from an actual SDE. And so we can define then the order of this convergence, kind of just giving us how fast a certain scheme gives us an acceptable pathwise convergence by this parameter gamma. And so we'll say that something is convergent to order gamma. And then we also have weak convergence, which is more useful if you don't necessarily need pathwise things, you're not directly simulating something, but you want to know more general characteristics of the SDE, like its moments or some kind of PDF. And so here we can use this parameter beta to give the order of convergence. And so just to get our hands dirty a little bit with these definitions, I'm just going to show you a simple derivation of the convergence for a geometric Brownian motion using the Euler method. So I'm just defining the iteration as we did before, and then showing that actually the convenient thing about geometric Brownian motion is that the numerical estimate is simply just the product of each of these estimates. And so then we can just quickly put this into our definition, and we see that, okay, well, to find this order with respect to t, we should probably first Taylor expand this exponential. And so we find that this Taylor expansion, just like any other Taylor expansion you might have done, we go out to order t squared, and we find that essentially we actually have the original estimate within this exponential, as one might expect. And so then what we want to do is, of course, we want to put this estimate in respect to the exponential, and then actually calculate out what our estimate is going to be based on this. And so we find then that the total error that we get is actually going to be order t to the 1/2. So Euler works well if we have relatively constant mu and sigma, but a lot of the SDEs that we are going to study don't necessarily have that property. And so what we want to end up doing actually is to apply Ito's formula to mu and sigma themselves, and then expand out this expression. And so for convenience, I'm just going to define the operators that we used in class. And now we're going to go through the first expansion of the Ito-Taylor expansion. And so what we do is, okay, we just have this integral equation, and we've now replaced mu, which is obviously a function of x, with the Ito's formula for mu, and same thing for sigma. And so what we can do now is we can take out the constant terms, and then we have a final remainder term, that is the double integrals essentially here. And so what we find is that there's actually one term which is order dt. And so we find that if we expand this term out, it is equivalent to sigma sigma prime times 1/2 times delta w squared minus dt. And so this actually gives us now the next order up, which is the Milstein scheme. It's generally considered equivalent to the Euler's, the deterministic Euler scheme, that is, because it actually has a strong convergence of order 1, as well as, of course, a weak convergence of order 1. And so this is an introduction to the world of the more general Taylor schemes, and we can find these schemes just by doing the same expansion and iterating.
Now that we've covered some of the basics, let's move on to another numerical scheme, the Runge-Kutta method. The setting here is the same. We'll be solving the one-dimensional, time-homogeneous SDE that you see on the screen, subject to the initial x0 equals x, where x is just a real number. Previously, we derived the Euler-Maruyama scheme, in which the stochastic process at the next time step is equal to that at the current time step, times mu of xn delta t, plus sigma of xn delta wn, where delta wn is just a random normal variable of mean 0 and variance delta t. Let's call this EM for short. Now, Runge-Kutta does a couple things to increase the accuracy of this, because unfortunately we still have a remainder of the order of the time step itself, delta t. The first thing it does is work with an approximation to the derivative sigma prime of xn. And we're just going to go ahead and rearrange the term sigma of xn plus 1 equals sigma of xn plus sigma prime of xn, sigma of xn, wt. And since this is a first order approximation, it's still of the order of a time step for the remainder. Now, the second thing we do is that we use the following approximation for the next time step. It turns out we can write this as approximately xn plus sigma of xn wt plus, again, an error of the same order. Now, substituting 1 into 2 actually gives us this nice expression, xn plus 1 equals xn plus mu xn plus sigma of xn delta wt plus sigma prime sigma, the integral from 0 to t of wt, dw of t, plus an order of delta t to the 3/2, which is now a much nicer order. In fact, we went ahead and substituted both of these things into the Euler-Maruyama scheme, EM. There's two more things we need to do to get the final Runge-Kutta form. The first is that we calculate this integral explicitly. And it turns out this Ito integral is just equal to half times delta w t squared minus delta t. The second thing is that we use the following extra step to approximate sigma prime. And this will come in use for cases where we want to model a stochastic process, but sigma prime is really hard to compute. So we write, or we define actually a new variable, xn hat, and we'll see that if we write xn hat is equal to xn plus sigma of xn squared of delta t, we can find out that sigma prime times sigma just becomes equal to sigma of xn hat minus sigma of xn divided by square root of delta t. And substituting this back into our equation over here, which I'll call star, gives us the following final Runge-Kutta scheme. You can see that at every time step, first we have to calculate xn hat, and then secondly, we go ahead and plug that into our expression for x at the next time step. Now this actually has a couple of decisive advantages over the Euler-Maruyama scheme. First is that it's of strong order 1. Compare this to the EM scheme, which actually has strong order half. And this also has a weak order of 1, which is comparable to the EM scheme. Look at the appendix from detailed proofs of these facts. Now, there are a number of ways to further increase this order, and you'll see this in the final part of the video, but let's just go ahead and apply this to a nice model. The first one is going to be of population growth. And this is a population model that's derived from the logistic equation, but adapted to a stochastic process, or a stochastic setting. And you'll see this is the following. Let's write lambda minus xs ds plus the integral from 0 to t of the square root of xs dw of s. Now, 2 words on the parameters. First, beta controls the growth rate. It can be a constant or not a constant. In fact, in the code that we'll see in just a moment, this is seasonal, so it could be something like sine of t to reflect the different growth and decay rates of populations with the year. The second is lambda, and lambda is the carrying capacity. This is basically the, this is basically the maximum amount that the environment can reasonably sustain a population at. I'm just going to go ahead and show the code, and let's go ahead and simulate it. You can see over here that I used a carrying capacity of 6, and as for beta, I used a cosine function plus 1 to ensure that it's never negative. If we go ahead and run this code, which you can also check out in the appendix to run for yourself, we'll get the following graph, something like this. You can see that if we started from just close to an initial condition of 1, it rapidly increases to its carrying capacity, but then the effects of seasonality occur. And you can see, again, a marked decrease of 2, up to a population of around 2. And then following, more waves until we get back up to around 6, it decreases again with the time, and this is just simulating from 0 to 20. A final thing I wanted to note is that sometimes the population could go extinct, especially if the carrying capacity is much too close for the variations in terms of seasons, in which case you'll find a graph that decays to 0 and stays there.
So now I'm going to talk about a topic called extrapolation. And the goal of extrapolation is to take an approximation and basically make it better by repeating it. So what I mean by that, if delta greater than 0 is our step size, and we denote x delta to be our discrete time approximation at that step size, suppose that this approximation is order 1. Then we define the value v g2 delta t to be 2 times the expected value of g x delta t minus expected value of g x 2 delta t. So what these quantities are on the right hand side is our approximation for the expected value of g of x of t, right? So x delta of t is approximating an Ito process xt. And so we run it once on the timescale delta and another time on the timescale 2 delta, and what we get is that this is actually order 2. So in general, we have the following theorem. So given a order beta approximation, to an Ito process on 0t, and a sequence of step sizes delta k is dk, so they're all a multiple of this step size delta, where the dk are increasing, and we have beta plus 1 of them, each of them is finite. Then we can get an order 2 beta approximation given by the following. Vg 2 beta delta is the sum of ak times the approximation at each of these scales. Where the AKs are defined to be any sequence such that the sum of the AKs is 1, and we have this relation. AK times dk to the gamma is 0 when gamma is some multiple of beta. So just to go over what this says again, if we have an order beta approximation, we run the simulation beta plus 1 times, and then we can obtain an order 2 beta approximation by taking some sort of weighted average of those approximations on each of those timescales, each of those timescales. So here I've plotted the error using a Euler scheme versus extrapolating that same scheme on an SDE that I could explicitly solve. So I used the geometric Brownian motion, and you can see so on the bottom scale here we have the log base 2 of the time step. So as the time step gets smaller, the error gets smaller as well, and we see it's double the slope of the Euler approximation.